Okay, welcome everyone. So today I'm going to talk about Z2 gauge theories. Hopefully, I'm planning this to be the last lecture on this topic. And the next topic will start on Monday is Luttinger liquid theory. That is theory of interacting particles one dimension. Before we go on to more complicated types of topological phases, we need to learn a bit more about what happens in one dimension, because as we'll see, the other topological phases have edge states. They have excitations on the edge, which are described by a strongly interacting system, typically in one dimension. So we need to understand one dimension systems better. And so that will be the next topic. Also, it's almost time to start thinking about your final course presentation. I'll write something on Slack and email this weekend on how you should proceed about it. Basically, it'll be 30 to 40-minute presentation that you make on PowerPoint, and you give me a copy of the PowerPoint, and then I'll find a time when you can make the presentation to me and any classmates who choose to come. The basic idea is to pick some paper somehow related to this course and not related to your own PhD research, and read it and explain it at a level that your classmates could understand. Yeah, so it's fairly broad, so you can pick something you like to learn about and explain it to your classmates. All right, any questions? Okay, so let me get started then on the topic of the day, which is, let's see, share content. All right, so the topic is Z2 gauge theories, and I had explained this Hamiltonian last time. It came from trying to understand the fluctuations of our theory of fractionalization in a spin liquid, and we initially had this complex field Qij, and eventually we simplified it to this particular Hamiltonian, where there's a qubit on every link of any lattice. In fact, today we're going to focus on the square lattice. So there's a qubit on every side of the square lattice, and the X, L, and ZL are the Pauli operators that act on that qubit. Okay, and then this is a typical type of Hamiltonian. We'll take the simplest case where there's a product of Z operators around loops, like, for example, this loop here. And then there's what's sometimes called a transverse field, or that's acting on every qubit in the X direction. Okay, so this particular Hamiltonian, there's nothing, the only special property of it, and you can take many other Hamiltonian that have the same property, is that it has a gauge invariance, and quantum mechanically that's stated by the fact that there's this operator G sub I that you can define on every site, and G sub I is a product of X operators coming out of that site, and as we discussed last time, this G sub I commutes with H. It obviously commutes with this term, and it commutes with this, because as long as you take the product of the Z's around closed loops. And you can add other terms, infinite set of other terms, and everything I'm going to tell you is believed to be quite generic. There's a special case of this, which is called the Kitaev Hamiltonian, and that's exactly solvable for all states, but it has, that has both benefits and price you pay. There's some properties are non-generic, some are generic, but you can solve for them exactly. Here we won't be able to solve for everything exactly, but nevertheless, we'll then understand at a deeper level, you know, what's robust about it. All right, so we're just going to treat this Hamiltonian on its own right, and not worry about the connection to spin liquids for the most part. And we'll just begin by considering what's sometimes called the even gauge theory, where the GI are 1. All right, any questions on the problem as defined? So now this is a self-contained problem that we can now study. And in fact, this problem was studied first by Franz Wegner in the mid-70s, I think, 74. I don't know the precise chronology, but around the same time, I think a bit later, Wilson started thinking about confinement of quarks using what's now called lattice gauge theories. And these papers of Wilson and Wegner were the starting point of a whole subfield of physics called lattice gauge theory today, which in fact, for well-designed models, is the state of the art for computing things in quantum chromodynamics. So if you want to compute the mass of the proton, given some information about the quarks, you can do that in lattice gauge theory. Okay, but we're going to take this very simplest example here, which turns out to be relevant to the properties of spin liquids. So, any questions? Excuse me. So there's two couplings here, K and G, and so things are going to depend upon whether G is bigger or K is bigger. So let's just look at the two opposite cases. The connection to Wisons corresponded to G equals 0. And then we'll see in a minute that the eigenstates of this part of the Hamiltonian at G equals 0 are indeed just the Wison states. So what is the ground state of this Hamiltonian? Well, basically, you got to make sure that the product of, you can put everything in the Z basis, and you just have to make sure that the product of all the spins around every plaquette is 1. And the simplest way to do that is to take, oh gosh, don't die on me now. That's moving. The simplest way to do that is to take all spins up. Okay. The only trouble with that state is that it doesn't satisfy this constraint. When you hit G on this state, some of the spins will flip. So my claim is that you can fix that by just multiplying this all spins up state by product on I 1 plus GI. So GI is an operator whose square is 1. That's one very important property. GI squared as an operator is always 1. Okay. So when you just from this definition, you don't need to even know that constraint. So now if you hit GI on this will give you GI plus 1, and so it'll go back to itself. But let's draw a picture of it. So this is the state with all spins up here. Oops. Okay. I erased something. Okay, so this is the state with all spins up. And then I hit a GI on this side. And then I flip this the spin on those sides. And now I'm only drawing the minus spins. In fact, I can even dispense with drawing the minus spins. And what I'm going to do is draw a line through every link that has a minus spin. So I draw a line here, and what I see is I get a square. And then you can quickly see, if you take all of these terms and expand it out, what you're going to get is all possible closed loops on the lattice. So every one of there's an infinite set of terms, really 2 to the n terms, where n is the number of sites. And if you just look at those terms, every one of them correspond to some closed loop, and vice versa. There's a one-to-one correspondence. So everything is just the sum of all closed loops on the lattice. So the wave function is, in this gauge invariant formulation, rather complicated beast. It's an infinite number of terms involving each term labeled by some loop packing. Now, they don't have to be close packed. There's some configuration of closed loops on the square lattice. Okay, so that's the ground state for G less than K. Of course, all of these terms are gauge equivalent to each other. They're just gauge transforms of each other. So they're not going to be essentially different, and so the calculations are not that bad. You can just work with this one component, and then you can be pretty sure that all the others will behave in the same way. Okay, at least on an infinite lattice. Okay, so now we look at the opposite limit where g is much bigger than k. Well, then this term dominates, and everything will point in the x direction. And so all spins are, say, pointing to the right, where they have eigenvalue +1. Okay, so those are the ground states. You know, they look very different, but there isn't obviously some symmetry that's broken because, for example, in this expansion here, there's equally likely to be a plus plus all plus. There's also a term with all or minus. So up and down are equivalent. You haven't like broken a symmetry or anything. So it's not at all clear whether there is these two limits could be smoothly connected. They could be. Okay. So now let's look at the excited states for G much smaller than K to begin with. So now to get an excited state, you have to have some plaquette, because the plaquette terms are the most important, where the product of the Z operators is -1 around the plaquette. So I have shown here a picture of a state in which there are two plaquettes, this plaquette here and this plaquette here, where the product of Z operators around that plaquette is -1. And to get that state, I had to flip the spin. This is on these green bonds. All of the green bonds really have a flip spin, but these plaquettes don't matter because the flux or the product of the Z's around them is still +1. And the actual wave function is not, this is just a component of it, but the actual wave function, as before, will have a product on I, 1 plus GI acting on this. And what you will then find when you act on this by this GI, you know, the location of this this frustrated plaquette and this -1 plaquette here will remain the same, but the string will move all over the space. There'll be a string and it'll be fluctuating wildly. It could be anywhere. It doesn't matter. Those are just different components of this wave function after some gauge transformations. Okay, this is just one possible configuration of the string connecting these two objects. And these are obviously the Visons. So they come in pairs, and there's a whole gas of them as you turn up G from non-zero values. And that's precisely what this is designed to. It's designed to answer what happens when these Visons start behaving like quantum particles. Okay. So now so these are the states at G equals 0. This is an excited state at G equals 0. You can take Visons anywhere. You have to take a pair of them, and this is the lowest excited state. And the energy doesn't depend on how far apart they are or anything. But of course, that's not true at first order in G. So now you do perturbation theory to first order in G. And when so here, for example, you have really a whole bunch of degenerate states where you have two Visons and they can be anywhere. And all of those states have the same energy because they have precisely two plaquettes, each of which cost an energy of 2K. So the energy of the state is 4K, and it doesn't matter where the Visons are. So you have to do degenerate perturbation theory. So you have a whole bunch of states at, so let me draw that here. You have the ground state, which is unique. And then you have a whole bunch of states here of order, the number of places you can put the two Visons. And this difference is 4K because, no, let's see. Yeah, it was -2K and then it became +2K. So this costs you 4K. Okay. But there's a whole bunch of degenerate states. And now this is at G equals 0. So if this axis is G, these states are going to split apart. And you have to figure out how they split apart. And there's other excited states there, but we don't worry about them. So first order in G, you just do degenerate perturbation theory in this degenerate manifold. And how do you do that? Well, basically at first order in G, you can find that the Vison will hop. So if you just flip this spin. Suppose I flip this additional spin here at first order in G from the X operator, the Vis-on will now be here. And so there's like a tight binding model. A Vis-on can from hop to 4 possible states, and so you can figure out the dispersion and helps figures out the momentum eigenstates that are going to appear here. So that would be a homework problem to carry that out. Okay, so that's for G much smaller than K. What about G much bigger than K? Okay, so at G much bigger than K, the ground state had all the spins pointing to the right, and that's all automatically gauge invariant. GI acting on it is still is +1. It's an eigenstate of the operator GI. But now you could ask, well, what are the excited states? Well, you could flip just one of them, but now the product of G around them is -1, so this doesn't seem like really an allowed state. Furthermore, if you, yeah, okay. I mean, so you could imagine fixing it by doing some gauge transformations. And I just, yeah, okay, I think you can, but anyway, but another problem with the state is if you try to make it move, here we hit the X operator and just moved one side. Here, since I'm doing perturbation theory in K, I have to hit the K operator. So suppose I hit the K operator on this plaquette, then I'll flip all 4 spins because the Z operator flips you from right to left. And so I'll get on this plaquette, well, sorry, I guess I'm hitting it over here. So if I hit it over here, this will flip back to right, and now only draw the left spins on the right-hand side and have 3. And this is taking you out of the manifold. And if you try to figure out, can I come back to the state, there's really no way to do it except by killing these. So and you can't move this thing. So this thing is really not mobile. So we just try to figure out what's the smallest thing that's mobile. That turns out to be 4 of them. And this, in fact, obeys the gauge constraint. GI is 1 because there's always an even number of left spins on every side. Yeah, okay. And now if you apply the plaquette operator here, you'll get this object. And then if you apply it once more, you'll get this object. And what you've done is just move this object from here to there, 1 step to the right. So you have to go to second order in perturbation theory for this object to move, and another homework problem would figure out the dispersion. So this, as you know, when you start thinking about gauge theories, this as we'll see in a minute, this is the confining phase. So there's a pure gauge theory in the confining phase, and the gauge excitations in the confining gauge theory are sometimes called glue balls. So if there's the glue that confines the particles in quantum chromodynamics, and then there is an excitation which you can measure in the accelerators called a glue ball. So this object is the toy model of a glue ball. Okay. But I'm just turning the crank here and doing simple perturbation theory in both limits. All right, so now comes the key question. We have understood something about the ground state and the excited states in the 2 opposite limits. And now the question is, can we connect them smoothly? Are these the same phase of matter? Are they different phases of matter? And of course, I've pretty much said the answer is they're different. And the first person to realize that was Wegner in his first paper. So as you turn up GC, what Wegner showed through different arguments that I really won't go through here, in fact, through a duality mapping to the Ising model that I think you have already or will cover in section, that there's a critical GC. And the large G phase, which I have called the confining phase, is very different from the small G phase. And how do they differ? Well, they differ by not a local order parameter, but by a non-local quantity, which is now called the Wilson loop, even though it was introduced by Wegner. So let's call it, both of them start with W. So, okay. So let's call it the W loop. So you take a big contour on the lattice, C, and associate with the contour on the lattice, you take an operator, and that operator is Z sub L for L belonging to the contour. Okay, so it's just the product of Z, 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 Z on this contour. Okay, so you take a big loop, and then you measure the expectation value of this operator. Look at the expectation value in the ground state. Okay. So that's the expectation value of the Wegner-Wilson loop. So what you can show that by exactly these methods that I've just been describing here, that for very large, so first of all, this is a gauge invariant object. You can see that this WC commutes with all the GI, again, because it's just defined on a closed loop. And if you look at the expectation of WC in the confined phase, it's exponential minus some number times the area of enclosed by the contour. So that's called the area law phase, the confinement phase. And how does that work? Well, you can just try to actually do the calculation in perturbation theory, and you'll see that that has to work out that way for very large G. So where was I? That's yeah, here. So let me add another page. Yeah. So you're going to compute the Wegner loop. So basically you have Z operators everywhere. Z, 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 Z. And the ground state, the state that you want to compute it in, 0 has the spin pointing in the X direction. Okay, so that's the simplest ground state. It's also gauge invariant. And it's easy to see that to this leading order in perturbation theory, that this expectation value of the Wegner-Wilson loop in this ground state is just 0 at G equals 0. Because the expectation of the Z operator in the right spin, we know that this is just 0 for, I'm sorry, this is, let's say, product on all the links of the lattice, and all of them are pointing to the right. All right, so how am I possibly going to get a non-zero value? Well, you have to do perturbation theory in the Hamiltonian and do perturbation theory in the ground state. So that's a very complicated task. But what you'll see is that when you do perturbation theory, you're going to modify the ground state by some powers of k. So every time you do perturbation theory at first order in k, for example, this is for very large G, so k is small. So when you do perturbation theory in k, you'll bring down product of Z around a plaquette. Okay, so say you go to first order in perturbation theory, then maybe you bring down a Z on this plaquette here. So now you have two Z's over here and two Z's there, and Z squared is 1, and so that will give you some expectation value. But the others will still give you 0, so you're not done. So pretty soon you realize that you have to put a plaquette everywhere. You have to go to you have to put these plaquettes everywhere, and I'm pretty sure I'm getting tired of them. So what you'll find is that this, if you take the exact ground state and look at this, this is not equal to 0 only at order k over G. That's your expansion to the number of plaquettes, which is the area of the sample of the loop, sorry, in perturbation theory. Okay, and so that's, so there you get the e to the minus area behavior. So that's the behavior which we've pretty much proven in the large G phase, that you get an area law for the Wilson loop operator. Okay, you can try to do the same calculation at small g. It's a bit more complicated, and I won't go through it. It's, I guess I can, there are references in the reading to a review article by Covert, which goes through it. And the answer is that it gives you a perimeter law, not an area. The expectation value of this, or maybe it's obvious, I don't remember. Okay, anyway, so I'll leave that as a homework problem to check that this is a perimeter law. Okay, so now we have this observable, which has a very, very different decay, and is a highly non-local observable. As the loop becomes bigger and bigger and bigger, it decays much faster here as the area enclosed by the loop than over here, where it's the perimeter of the loop. And so these two behaviors cannot be smoothly connected, and that was Wegner's argument for a phase transition. Okay, and this area law behavior is characteristic of confinement. If you think of this loop as a pair of quarks and anti-quarks in space-time, then this area law tells you that there's a potential between them that depends on the linear distance between where you separated the quark and anti-quark. All right, so that historically was extremely important in showing what a confinement phase was, but also giving you an example of a confinement-deconfinement transition. So in our spin liquid language, what's happened is that here you just had lots of visons which were floating around. And then at some point, the visons, as the terminology goes, they condense. You get so many visons that the whole system just points in the X direction effectively, and you lose your deconfined physics of these and the fractionalization that were behind the whole vison description. Okay. Now, I would spend a lot more time on this, and maybe there was a time when there's a huge amount of discussion on these Wegner-Wilson loops. But it turns out there's a modern way of understanding this, which is quite a bit superior, and it's what people now use. And one of the issues is that this particular distinction between the two phases of this loop operator only works when you don't have what are called matter fields. Or in our language, for our case, it'd be like if the spin-ons had a finite energy, or the quarks were around with a finite mass, then you find that there is in fact never an area law phase, because as you make the loop bigger and bigger and bigger, you create a bunch of quarks in the center which break the loop into separate components, and that's what would happen in real life too. If you took a quark and an anti-quark and you pulled it apart, eventually the vacuum would create a quark-anti-quark pair, and you'll be left with two mesons, which will be free to move apart. So that's what happens to this once the mass of the quark is finite, or once the gap to the spin-ons. If you put spin-ons back into this theory, you'll find that there's never really an area law. Okay, so but the fact that there's a phase transition still survives when the spin-ons have a finite gap. So, when I was learning about this confused me the greatest deal, that okay, once the spin-ons have a finite gap, how can you still talk about a confining phase? Anyway, so now we talk about it not using the Wegner-Wilson language, but by the important characterization of the topological phase. So this phase, this deconfined phase, has what's called topological order. And that's really the best way to distinguish the two of them, because it's a very robust distinction, which is valid even when you add matter fields. And it can tell you whether you have a phase transition or not in the presence of matter fields. So what is topological order? So again, we want to go to this phase here, where G is much smaller than K, and figure out the ground state. And the key thing you want to do, which Wegner did not consider, is to look at the ground state on a torus, or any two-dimensional space with a non-trivial topology. You put on a sphere or multi-handle torus, whatever. So we'll just take a torus. So here's my picture of the torus. Okay. So what happens on the torus is that it turned out to be new operators that commute with the Hamiltonian. So far I've asserted, and this is correct, that for this type of Hamiltonian, the set of G's exhaust the set of operators that commute with the Hamiltonian. That is, all the operators that commute the Hamiltonian are either the G's or the product of the G's. You could take G1, G2, G3, G4. That's an operator that will definitely commute with the Hamiltonian. So G's generate all the conservation laws. But when you put it in a torus, that's not true. They turn out to be two more operators that commute with the Hamiltonian. I'm going to call them Vx and Vy, and here's what they are. Okay, so here's a picture. Now imagine that this square here is a torus. So I made this picture at a time when I was still using the Pauli matrices. So excuse me, I didn't update it. So sigma x is the x operator, sigma z is the z operator. So what is the v operator? Well, the v operator, like the g's, is a product of the x's, but it's a product of the x's, not on all the sites coming out of a link, but it's a product of x's on all the links. So in this case, Vx is you take a link that goes around the torus. Okay, so it's a product of x here, 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 and so on. Take the product of x's around the torus. Okay, in the x direction, and you can take it in the y direction. And in fact, you can take any contour you like, and you can quickly see that you can move the contour around by just multiplying with the g's. If I multiply with the g over here, then the contour will just go like that. So there's only two new operators for one contour encircling the torus in both directions. And notice this green line is drawn on the dual lattice. So that's what the bar is supposed to remind you. The green line is drawn on the dual lattice, and there's two dual lattice contours in the x and y direction. Okay, now it's easy to see that why this commutes with the Hamiltonian. Well, it commutes with the Hamiltonian because it intersects every plaquette twice. So when I take the z's on this plaquette here, it'll have a z and an x there and a z and an x there. All right, so you can this is true. So there's two new conservation laws on a torus. All right, so this is in fact not the Wilson loop operator. This is when you generalize it to other things, it's sometimes called the 't Hooft loop. So this is the analog of the 't Hooft loop operator, the Vx and Vy. Okay, so it's also useful, although they don't commute with the Hamiltonian, to introduce the Wilson loop operators, which are Wx and Wy. And these are Wilson loop operators that encircle the torus again in either the x or the y directions. So there's two special Wilson loops that go all the way around the torus. Okay. So these are just, you can pick two of them and we'll just keep them around. Okay. And so now another crucial thing is that the V operator in the x direction and the Wilson loop operator in the y direction anti-commute with each other. So there's a very simple operator algebra. Of course, we have the square of these operators is 1, as always. Vx squared equals Wy squared equals 1, and so on. But then they anti-commute with each other. So they're basically like Pauli matrices. There are these two operators, the Vx and the Wy, are like two x and z Pauli matrices. And so their representations, when they act, will form a qubit. So there's some gigantic qubit associated with a operator that encircles the entire loop of the torus. Okay. Oops. Where's that? And similarly, the other way. So there's two qubits, one associated with Vx and one associated with Vy, and Vy anti-commutes with Wx and Vx anti-commutes with Wy. And why do they anti-commute? Well, okay, let's just look at the Vx operator. This is the, so the Vx operator is on the green line. So on this green line, I have a Vx, and then I have a Wy on this line. And you can convince yourself that the Vx and the Wy intersect an odd number of times. You could take a very more complicated contour, but so one is going this way, the other is going that way, and they're guaranteed to intersect an odd number of times, and that's why they anti-commute. Okay, so we have these operator algebras, and it'll turn out these play a crucial role in understanding the structure of the ground state. So we want to be in the topological phase. It's like 2 minutes, you can see that there's nothing interesting going on in the large G limit. All the fun is in the small G limit. So in the small G limit, I told you what. Hello. Oh, sorry. I told you what the ground state was. It was just all spins out, and let's not worry about the 1 plus Gi. That won't do anything. Okay, so that's the ground state. And it's an eigenstate of both Wx and Wy with eigenvalue 1. Well, because it's the product of Z and all the Z's are up. Okay. So that's the ground state we had. But now I can construct some other states, which are in fact orthogonal to this state. And one of those states is Vx times 0. So what is Vx times 0? Well, Vx is going to do is flip the spin on this green contour. So every link that intersects the green contour will have its spin flip from up to down. Okay, so the spins on that contour will become minus when I hit Vx on the ground state. But now you can see the flux through any plaquette. So this plaquette and this plaquette is still +1 because it intersects every contour an even number of times. So this has exactly the same energy. So I've discovered another state which has exactly the same energy by using this contour that encircles the torus on the x direction. So one thing you might ask, is this state a new state? Maybe it's the old state. Maybe it's some linear combination of the old state. And there's the simple way to figure out that it's not, using this anti-commutation relation. Because let's look at the eigenvalue of Wy. The old state, the eigenvalue of Wy was +1. In the new state, easy to see, the eigenvalue of Wy is -1. So therefore, there's got to be a different state because they have different eigenvalues of Wy. So I found a state that's orthogonal and has the same energy. So I have a double degeneracy of the ground state. But of course, why stop there? So yeah, here's the state Wx of 0. I guess I tried to draw that there. You just flip the spin everywhere along this line, and that gives you the orthogonal state. You can also do Vy, and you can do Vx, Vy. So there are actually 4 ground states. So this is the famous 4-fold degeneracy of the Z2 Gates theory on a torus. So these ground states are eigenstates of Wx and Wy. They're not eigenstates of Vx and Vy, but there's no problem to take linear combinations of them, as shown here, to make them eigenstates of Vx and Vy, which is what they should be, because Vx commutes with the Hamiltonian and Vy commutes with the Hamiltonian. But notice when G is non-zero, they're not. It's not going to commute with the Wx and Wy. That doesn't commute with the Hamiltonian. Okay, so that's at G equals 0. So at G equals 0, what we've said is that there are 4 degenerate ground states on a torus, and they're separated by some energy about a k from all other states. Okay, So now, okay, but that's a trivial state at G equals 0. What's going to happen at non-zero G? Well, again, the argument is similar to the Wilson loop type argument. So G equals 0, they were separated from all other states. So really all I have to consider in doing degenerate perturbation theory is matrix elements of the Hamiltonian within these states. I don't want to go out of this manifold. So I have to ask, how large is the matrix element between two of these states? So now if I look at this, here's the state, one of the ground states, which has flipped spins everywhere on the dashed lines. So on the dashed lines, I have a minus spin. And the other ground state has no lines, has all spins up. And suppose I want to connect them in perturbation theory. Well, the only way I'm going to connect them is if I hit the transverse field term, the G term, L times, once here, 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 and so on. Of course, the best thing to do just will be take a straight line. That will give me the first answer. So if the length of this is L, the off-diagonal matrix elements between these states only appears at Lth order in perturbation theory. Okay, so which is then exponentially small because G is small here. We're doing perturbation theory. So this is e to the minus L. So this degeneracy, while not perfect, is very, very good. It's exponential in the length of the sample. Excuse me. And so the length, as the length goes to infinity, these states, four states, become degenerate. And that's a robust property of the deconfined phase. And that's in fact what we call topological order. The fourfold degeneracy of the ground state. And these operators, these ground states will no longer be eigenstates of Wx and Wy, at least to this accuracy, but they will be eigenstates of Vx and Vy because they have to be, because Vx and Vy commute with the Hamiltonian. So in general, there are some complicated linear combination of these four states, the ground states. And those four states, what are these four states? Well, the four states are the eigenstates associated with these two algebras. So you have an algebra here of Vx and Vy, and another Pauli algebra here. You have sort of two sets of Pauli algebras giving you a total of 2 qubits or 4 states. And the W operator is a raising and lowering operator between two of them, and the Wy operator is something like it, and the Wx operator is raising and lowering operator between the other two of them. Yeah, no, it is in fact. It just flips you from Vx equals +1 to Vx equals -1. So these 2 qubits, this is the heart of the idea of topological quantum computing, or in this case, actually, it turns out to be just a memory. So if you now take some linear combination of these 2 qubits, and somehow you prepare it, don't ask me how, but somehow you prepare it in some complicated linear combination of these nearly degenerate states, it's going to be insensitive to any operation, any local operation, because the only matrix elements that connect these states together has to wind around the torus. So if you have some noise or some dirt or anything, as long as it doesn't go all the way around the torus, it's not going to destroy the coherence of these 2 states. So that's the very crudely stated the idea of topological quantum computing or topological protection. The Hilbert space of these 2 qubits can only be disturbed by operators that have to have wind around all the way around the torus. But that's also the problem. You can, how do you then actually flip this qubit? Well, that's not easy. So, but you have to then also design an operator that will do it. Okay, so there's some topological error correction here, and the operators that wind around the torus are your, logical operators.
I'm sorry. This may be a very like naive question, but like, how do I see that in order to disturb this Hilbert space, I need to like go around the torus? That's something local cannot do it.
Well, because any such operator will not really take you out from these two states to something outside, something above. It'll just take you up there, and those are high energy states. So they're basically virtual type fluctuations. They're not going to change the precise linear combination of states that you have between the states in here. Yeah. Right.
Okay. Thank you.
So, we also get these ground state degeneracies in the case of spontaneous symmetry breaking. I guess if it's like so what's kind of like the crucial difference here?
With there you can, I mean, with spontaneous symmetry, well, okay. Well, you mean in the Ising model, there's two states there.
Yeah, exactly.
Yeah, so there, if you just put in a local magnetic field somewhere, it will not be exponentially suppressed. I mean, the local magnetic field will change the energy of one of them by order 1. If you put an up, you have two states, all spins down and all spins up. And then on site 0, you put a magnetic field that gives you energy of order 1 between state 1, the first state and the down state. So the difference in energy become 1 between them because of the very local field. So the total energy is of order n, but the degeneracy will be lifted by an energy of order 1.
I see. So you're saying there's no local operator that could lift this degeneracy?
No, there isn't. I mean, that's exactly the argument we just went through. We have these states which only differ by a very non-local operation. So any matrix element that's going to act with the degenerate subspace has to really go all the way around.
And is that the defining feature of topological order?
The presence of gap degenerate, yes, it is for gap state. The fact that the degeneracy of the ground state, here by degeneracy I mean up to terms about the e to the minus perimeter. The degeneracy of the ground state depends on the topology of the manifold you're sitting on. And that's also not true for spontaneous symmetry breaking. If you have spontaneous symmetry breaking upspin and downspin, whether you put it on a torus or a two-ring torus, it's always 2. It doesn't depend on what. So in fact, this thing, what will the degeneracy be? So suppose I had a 2-hole torus, which I'm going to make a brave attempt to draw. So, suppose I had this object, this thing. Now the degeneracy, somebody can tell me what it is. There will basically be, I forget. There's going to be 2 qubits here and 2 qubits over there. So degeneracy maybe 16 or maybe it's 8. I'm sorry. You just have to figure out the total number of independent.
Go to the 4. 16.
Huh?
Yes.
So 16. Okay. Okay. So this genus, genus 2 object will have a different degeneracy from a genus 1 object and so on. Whereas for spontaneous symmetry breaking, that's not true. It will be the same on any manifold. For an Ising model, the degeneracy of the ferromagnet is 2. It doesn't care about the topology of the manifold.
Okay, that makes sense. Thank you.
Yeah.
Here you mentioned above that like this is not a symmetry breaking sort of order. So is this what people like call higher form symmetries, or because the charge operator is large? Okay.
I don't. Well, there are some kind of, maybe Juan can answer this better. So yes, this Z2, it's dual to a 1-form Z2 symmetry or something. Is that right?
Yeah, let me say this. Who asked the question? Darshan? Who asked?
Okay.
No, I just want to know who is the person asked, so I can call his name. Akira?
Yeah.
Akira. Okay, Akira. A very good question. Well, I'll be brief. the example Subir said is Z2 gauge theory or the Z2 topological order or spin liquid. There's a Wilson line from the wall line of this electric particle. So that's actually has charge under one phone Z2 symmetry. While also the topo line also is charged under another one phone Z2 symmetry, and one is co-electric, one is magnetic. But what do we mean by the charge object for this line operator is exactly just generalized the way we view the global symmetry. As Subir tried to say, when we try to discuss global symmetry, we take some usually unitary operator here and commute with Hamiltonian. But the unitary operator need to act on all the space, right? All the space. You apply this operator, maybe tensor product of operator X on side, but you have to take the whole operator X on the whole space.
Right.
But here, then that define the notion of this symmetry operator, and they can measure the symmetry charge locally on some local operator. So that's called the usual symmetry. These are the usual global symmetry, zero phone symmetry. While the one phone symmetry, the example, the good one here for the Z2 torical that we discussed, is the charge object is actually the line operator, or the magnetic Tohu operator, but they are actually mutually charged under each other, in the sense that the electric line has one phone Z2 symmetry charged, but can be measured by magnetic line operator, while the magnetic line operator is charged and then by the other one. Yeah, that's basically. Yeah, let me just say because these are get a lot in there.
I'm not following either, so let's.
You're not follow? I saw some people still follow.
Finish the sentence, please.
Yeah, the sentence is exactly the calculation what Subir tried to show when the EMN cross, there's a minus sign. If you view this EMN cross as minus sign, viewing the space-time pictures, it's basically two of the line operator from loops, two loops linked. That's basically a picture. But you can interpret this picture in terms of the modern language. Let modern language exactly say the two lines displaced in the time direction, such that one line is X direction, the other is Y direction, let's say, but they separate by some time difference. You can think about Hamiltonian picture. And that picture shows that actually this is exactly a measurement. One of the line operator, there's a magnetic line, Tohu line.
Okay, Jovan, thank you. I'm going to have to move on here. Thank you very much. There is some further comments on this in the notes on the readings, the connection between this and Chern-Simons gauge theories, and we'll come to that. The other comment I'll make is that these higher form symmetries are kind of statement of some conservation laws, but the statement of topological order is a more dynamical statement of a certain theory with a certain Hamiltonian has or a Lagrangian has a certain property, and so but they're related, of course. So these theories with these one form symmetries often do have topological order. Okay. All right. So I have 4 minutes left, and I do want to say a few more things and then close this chapter. So first of all, I've already said this earlier, that for G much bigger than K, there's unique ground state, which is all spins to the right. And you can quickly see that Vx, this is an eigenstate of Vx, and if you take Vx equals -1, that will put all the spins to the left, and that's a very high energy state as G is equal to V is so large. So there's no possibility of any degeneracy. So what's happened is that you have this very small degeneracy on one side and none on the other. And it's got to break down somewhere in between. And so there's some kind of quantum phase transition. And if you want to read papers on exactly how it breaks down and how you go from one limit to the other, that's in fact the thesis work of one of my students, Seth Whitsitt, and you can find papers on the website. In fact, I think they're probably linked in the notes. Okay, so I want to say a few more things. One is, what is the nature of this quantum phase transition? at G equals GC. So the simplest way to get it, which is the way Wegner got it, is to do the duality mapping. So the specific lattice model I wrote down with a plaquette term for K, just a square plaquette term for K, and a single term for G. That specific model is in fact dual to the Ising model in a transverse field, which is something covered in section already or will be. And therefore, we know the Ising model has a phase transition, which is just the Wilson-Fischer 5/4 field theory, as we discussed some time back. So this should have the same transition because they are the same theory. But even if you didn't know that, you could kind of wave your hands and understand this in a very simple argument. So the basic picture you have to have is that the Wison, as you increase, so at G equals 0, you have a Wison excitation. And as you increase G, the Wison becomes lower and lower in energy. At some point, it is 0. So all we need to worry about is the dynamics of the Wison field. Now, the Wison is its own antiparticle, so it's described by a real field. So we just write down a theory consistent with phi goes to minus phi, and that turns out to be the Wilson-Fischer theory. So when the Wison is gapped for R greater than RC, you have the topological phase with the fourfold degeneracy. And when it's not gapped, then you have confinement, and the Wison condenses with no degeneracy. And exactly how you go from here to there using this field theory and how the degeneracy of the manifold changes on the torus, or the ground state changes, and how the levels move around right near the critical point, that's something Seth worked on quite a lot, and there's information, the references. Okay, in the last 2 or 3 minutes, I want to make some important remarks about what about the other case, which is actually the case that started this whole game. That's the case for bosons at half filling, GI equals -1. All right, so you can repeat everything I said for GI equals -1, and then you find that actually there are some differences. For G much smaller than K, it's very similar. You just take all spins up, and then to make it gauge invariant, you put a 1 minus G. So then you can see its eigenvalue is under acting on G is just -1. Okay, so then you get the sum over all closed loops where you go, pick up a minus sign for each plaquette that you enclose. Okay, not so bad. Almost looks okay, looks similar. But what about G much bigger than K? Well, now you've run into a problem. So what I'd said for G much bigger than K is that all spins point to the right. Okay, if all spins point to the right, then capital GI is +1. So you've got to have some spins point to the left. In fact, you have to have one spin pointing to the left for every link associated with every side, or really an odd number. So here is the simplest state that is satisfy the constraint with the minimal number of lefts. You can put left here, 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 and here, 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 here. And this will have the smallest number of left pointing spins, so it'll be a ground state. And it will also satisfy the constraint, because on this side, there's one thing to the left. On this side, there's one thing to the left. On this one, there's one on the top, and so on. In fact, you can see, and I should remove some of these here. That's not the only one. There's a set of all dimer packings, in fact, and I made a mistake here. So this has got to go. Oops. So that has 1, this has 2. So I got to remove that for sure. And that has 1. This site doesn't have 1. So I can, where should I put it? I can put it over here, right? And then everybody's happy. Yeah. Now here's another configuration. No, that's got 2. No, that's not good either. Okay. So now that site has 2. So maybe here. Yeah. Yeah. No, that's not good either. So what am I doing here? Where should I go? Well, I'm in trouble. Okay. So let's put it over here. And then I got to get rid of this one. And that I'll put over here. Okay. So now you can see every site has only one marked link or a left pointing spin next to it. And you can easily see these are our valence bonds. These are all dimer configurations as before are the ground state. So every dimer configuration of the square lattice gives you every set of single bonds you can make gives you a degenerate ground state. It's quite beautiful how this picture reappears. Okay, now these states are all degenerate as k equals 0. So now you got to do perturbation theorem k over g. And that's a complicated business. I won't go into it. And in the end, it turns out that when you do perturbation theory, this state here, the valence bond solid state, this is just dimers sitting like this. Yeah, that's literally is the valence bond solid state that I'd drawn earlier. This one wins. So amazingly, the confining phase has valence bond solid order. And this actually better had worked out because there's a theorem called the Leaf-Schultz, Mattis, Oshikawa, Hastings, and maybe some other people theorem, which is the following: that for bosons at half filling, which we believe are the same as the Ising model at g equals -1, you cannot have a trivial ground state. That is, you either have to have topological order, which you do have in this case at small little g, or you have to have a broken symmetry, and which the valence bond solid order breaks. And actually this is good that this worked out, because we found when we started studying bosons at half filling that I couldn't make a trivial mod insulator. No matter how I tried to put the bosons in some local arrangement, I always either put them on a charge density wave or a valence bond solid. I couldn't do it. And that's exactly what you find here. In fact, that's a rigorous theorem, that you can only make a liquid state of the boson that doesn't break any symmetry if you have this fourfold degeneracy and this torus, these properties that we just discussed here. And so topological states are the only way at half filling to get something that doesn't break any symmetry. And that's the Leaf-Schultz, Mattis, Oshikawa, Hastings theorem. Okay, so I definitely wanted to mention that, and that's where this anomaly is absolutely crucial for getting the right physics. You have to put that in, otherwise you wouldn't satisfy this theorem. Now, the integer, when G was 1, that corresponds bosons at integer filling, we got a trivial confining state, all the spins pointing to the right, and that's like the mod insulator. It's trivial, one integer number of particles on each side. Okay, and the final statement, and then Juven, and maybe I'll open the questions by others. You can do perturbation theory in the non-confining phase with G is -1, and this may again be a homework problem. You'll find that, as we discussed last lecture, when the visons go around a plaquette, they pick up a phase of -1. And if you figure out the consequence of that on the dispersion of the visons, you find that the dispersion is doubly degenerate. So it's just a matter of diagonalizing pi flux hopping on the square lattice. And that may be something, it's quite easy and assigned as a homework problem. All right, so that's the end of our discussion of V2 Gates theories. It's amazing how much beautiful physics is residing in the Wegner Hamiltonian, and also how many years it took for the community to understand all this stuff that I've summarized in less than an hour. Okay, any questions from people other than Juven and then Juven? Sorry,
excuse me, LSM theory also have a gapless phase. I think I just want to clarify your statement. It also can be gapless, not necessary topological order. Also, other than symmetry breaking or topological order, it just requires degenerate ground states, right? So that's the statement.
That is the theorem in one dimension. I'm talking about 2 dimensions. That's where the LSM, you're right. So the LSM proved it in 1D. It was Hastings and Oshikawa extended to 2D. So I'm referring to the 2D case.
Well, okay, but the usual statement from Tehu anomaly doesn't rule out gapless phase though. So that's probably LSM theorem's more stronger than anomaly, Tehu anomaly, because I think gapless symmetry preserving is also allowed. That's
you're right. You're right. Yeah, no, I think you're right. You could get a gapless spin liquid. Yeah, no, that's not strictly speaking. In some people's definition, that's not precisely topological order, but it is in the sense it has. Yeah.
Just change the topological order to generally degenerate ground states, and that's okay. Gapless phase.
Right.
Otherwise, into a topological order or symmetry, or it can be gapless. It can be symmetry breaking gapless or symmetry preserving gapless, whatever. But just gapless is okay, or the symmetry breakingness, you say. Yes.
Thank you. I'm inserted that possibility here. So thank you, actually, Jovan. That's a good point, and we will see this possibility of critical gapless states soon after we're done with one dimension. Thank you. That's correct. Okay, other questions? Okay. Yes, go ahead, Yanting.
Does the theory also has a self-duality, like the Ising self-duality? Because it's dual to the Ising theory, right?
So all of these are basically the same set of dualities. When you do it in 1+1 dimension, it's a self-duality. The Ising chain is self-dual to itself. But in 2+1 dimension, the Ising gauge theory is dual to the Ising non-gauge theory. So it's not a self-duality. It's only self-dual in 1+1. And if you go to so in 1+1, the Ising gauge, the Ising non-gauge is self-dual to the Ising non-gauge. In 2+1, the Ising gauge is dual to Ising non-gauge. In 3+1, the Ising gauge is self-dual to itself, but the Ising non-gauge is dual to one form gauge theory. It's a higher form gauge theory. So there is a whole set of dualities but the nature changes with dimension.
Okay, so then this theory is dual to like a non-gauge.
Yeah, it's just the Ising model, right? This is what I stated here.
Okay.
So it's not a self-duality.
Yeah.
So the Z2 gauge theory is just the Z2 dual to the Z2 Ising model without a gauge field. In 3+1 dimensions, the Z2 gauge theory is self-dual. And in 1+1 dimension, the Z2 Ising model is self-dual. I think Jovan has the most general way of stating it. No, you're saying something.
In 1+1D, the Ising is dual to Ising coupled to a Z2 gauge field.
Just one Z2 gauge field, right? Yeah.
Yeah, but it's
I know. Okay, thank you. That's very important. Yeah, I was making statements in the bulk. If you really wanted to keep track of the full structure with boundaries, then there are some subtleties that I think you've been discussing in section. Is that right?
Yeah.
Thank you. Yes. Yeah, I mean, Ising is self-dual to Ising, not quite. There's just one global qubit you have to worry about. But it's not a thermodynamically significant correction. But that's crucial, of course. That global qubit is what leads to the Kitaev chain and and so on. So it's very crucial for some things.
I have a naive question.
Yes.
So for this quantum phase transition, this is for G I equals 1, it's a phase transition without symmetry breaking. But if I just look at the field theory, so you write this D5, it's a basic 5-4 theory. And if I just look at this theory, it gives an impression that this is a symmetry breaking phase transition since this is also
Yes.
in Fischer class. So how do I see that it's actually a topological phase transition by looking at this theory?
Well, that's a great question. One is that phi, the field, I can write on a field theory, local field theory, which seems to be breaking symmetry, but the field itself is not a measurable quantity because you never can have a single Vizon. You can only measure pairs of Vizons. So strictly speaking, this is sometimes called the Ising star gauge field theory. This is very much related to what Hayu just said. There's a global constraint you have to worry about. It doesn't change any thermodynamic properties or any critical exponents, but it does affect the spectrum on a torus. And so it's really, strictly speaking, it's not really the Ising model, it's some Ising star model where any local operator which has an odd number of phi's is not allowed. It's not part of the spectrum. Yeah.
I see. So all the order parameters and observables that one would construct in this theory will have even number of phi's all the time.
Correct. Yes. Yeah. Even though the exponents would be the same as the Ising model, many other things, the whole, for example, the spectrum on a torus will be different of this field theory than the Ising model field theory. Because, for example, you put this thing on a torus, then since phi is not measurable, then you have to allow for phi having a twist as it goes around the torus. That's whereas in other cases not allowed. Yeah. You have to sum over periodic and anti-periodic boundary conditions. So on. Yeah. Yeah.
Thank you.
Sure.
And so in the second case, when GI equals -1, it's also, so two kind of phase transitions coincide somehow. So you also have a topological phase transition because it's a confinement deconfinement of these Vizons, but also it's a symmetry breaking phase transition because the valence on solid basically breaks lattice translation symmetry. So how do I describe this phase transition now? Is it just a topological phase transition or?
No, it's a deconfined critical point. I don't, maybe we'll return to it later. It's in the notes on the reading. I have explained how to, it's quite an interesting critical point. In fact, I was the one who figured it out in 92. And yeah, so there's an interesting story there, but I'm not going to discuss it here. You can read about it in the notes.
Okay. Thank you.
It's a story very close to my heart. Yes. Are there questions? Okay, we'll have our Saturday morning discussion tomorrow. Please come, and I'm sure there'll be a lot of further discussion of these very interesting results. Okay, thank you.